In previous videos, we've looked at calculating the derivative of certain terms. So we've looked at calculating the derivative of simple singular terms on their own with coefficients. We've looked at calculating terms that involve square roots and negative values as a power. And then what we've looked at is expanding this beyond having just a single term to look at two or three terms combined together, simplifying these down and how we work through them. But there's no point in looking at this if we don't start to think about why. What applications of this do we have? And how can we use it? And the first of these that we're going to look at is something called rates of change. Now, whenever you see that phrase rates of change, the first thing that should spring into your mind is the derivative. Think back to when we introduced derivative. We introduced it as the gradient of a line. Now, the gradient is the slope of a line, and the slope of a line tells you the speed at which it changes. It tells you how the line changes as you're going. That's what derivative refers to. It refers to any form of rate of change. And that can include lots of others, including things like velocity. Whenever you see this phrase, rates of change, instantly you have to start thinking about the derivative. Now, what we want to be able to do is calculate the rate of change of a function at a set point. And in order to do this, there's a couple of easy steps to follow. First, you take the derivative, then you put in the value for the unknown variable at that point. Once you've done that, it's just calculating the numbers through. Easiest way for me to show you this is with a couple of examples. So let's imagine I tell you that given f of x equals 2x to the power of 5, find the rate of change when x equals 3. First thing you need to think about whenever you see that phrase rate of change is instantly think of the derivative. That's what I want to calculate. Now remember, when we said we're calculating the derivative, we want to write the terms first in the way that we want. So as ax to the n, those sorts of form. Well, this one's already written like that, 2x to the power of 5. So great, it means I can just instantly start by calculating f dashed of x. And again, remember with this one what we do, we write down the 2 times and then we take the derivative of that part, bring the power down, 5x, and then reduce the power by 1 to the power of 4. That then equals 10x to the power of 4 once we simplify it. Now, I want to get the rate of change when x equals 3. Once I've calculated the derivative, in order to do that, what I'm looking to calculate is f dashed of 3, i.e. what do I get when I substitute in 3 for wherever I get a value of x within my derivative function. So to do that, we simply plug it in. We get then 10 times 3 to the power of 4. Putting it in for x. 3 to the power of 4, that's 81. So it's then 10 times 81. 10 81s at 810. Once we've done it, this is the point where we look back at the question and say, right, what is the scenario? Because there may be units that have to come into play. Now this one's just a simple, find the rate of change when x is equal to 3, so we don't need to worry about that. But there will be times where we need to think about, is the question referenced in a scenario and what would we need to include in terms of units? So let's look at another example of that. So imagine given y equals 1 over cube root of x squared for x not equal to 0, calculate the rate of change of y when x equals 8. So it's the same sort of question. First thing we have to do is take the derivative, then we substitute the value in. Now looking at the function, what we have to do first is actually make this into a form where we can take the derivative. Think back to when we did that with differentiation. So first thing we do is we sort the root on the bottom. So that would give me 1 over x to the power of 2/3. We've then got 1 over x to a power, bring it up and we get a negative power. So we get x to the power of negative 2 over 3. Now it's in a form that I can take the derivative of, so now I take the derivative. So what I now look for is dy by dx. So I do dy by dx equals, and it's the same form for the derivative despite it being negative powers. Bring it down in front, reduce the power by 1. So I get negative 2 over 3x to the negative 5/3. Now because we're looking to substitute in a value, we now have to sort this so it's in a form where we can do that and actually calculate answers. So we start by getting rid of the negative, so shift the x underneath, and then we look to write it out how we can work with it. So I'd end up getting negative 2 over 3x to the power of 5 over 3. I then have to sort the x to the power of 5 over 3, so I get negative 2 over 3. Now over 3, remember that's the cube root, so it's the cube root of x, but then to the power of 5 as well. So that's me sorted it now to a form where I can actually physically do it. What I now want to do is calculate it when the value of x is 8. So what I now want is to do dy by dx when x equals 8. So in this case, substitute it in. So I get negative 2 over 3 bracket cube root of 8 to the power of 5. Cube root of 8 is 2. So I get negative 2 over 3 times 2 to the power of 5. 3 times 2 to the power of 5 gives me 96. So I get negative 2 over 96, which I can simplify down to get negative 1 over 48. And that's me got my rate of change at that point. And again, no context, no units that come into play with this question. So this is what we have to be able to do with that one. So we've calculated the rate of change of the function at that point. We could take this and work in context with it. So we can actually work with that. So let's have a look at a contextual example of it all. So let's imagine I've got the problem where I've got a ball is thrown, so its displacement after t seconds is given by s of t equals 23t minus 5t squared meters. Find its velocity after 2 seconds. Well, there's a couple of keywords we have to start thinking about. Those keywords are displacement and velocity. Now, I've said rate of change tells you about the way a function changes. Displacement, if you think of displacement of an object, that means position. If you think you've got an object and you want to know its displacement from the origin, so its displacement from the start, that just means what position is it at now. Where is your object? Where is it sitting? So displacement means your position. Velocity means speed. Velocity means how fast is an object going. So that's how fast is it going from this position to that position. So velocity is the displacement taken for the derivative, i.e. the velocity v of t equals the derivative of the displacement. It's the derivative of the position. So if you ever see those two words linked together, this is what it's referring to. It's referring to you calculating the velocity by taking the derivative of the displacement. So let's do that then. Let's take the derivative of the displacement to get our velocity. So we know v of t is going to equal the derivative of this. So start with the first term. We've got 23. Derivative of t is just 1, so it's just 23 on its own. Take away 5 times the derivative of the t squared part. So we get 2t to the power of 1, so just leave it as 2t. That then equals 23. Take away 10 times t. So we've got the formula for our velocity. We know what it is. What we now want is the velocity after 2 seconds, i.e. v of 2. So we substitute in 2 for wherever there's a t. So we get 23, take away 10 times 2, which is 23 minus 20, which then works out to give me 3. Now, I mentioned before about units. Well, look at the question. The displacement is given by units, the velocity after 2 seconds, so the time unit and our displacement unit are given there, which means our velocity has to be 3 meters per second. We have to include that in our answer to put it back into the context of the question. And this is a vital thing at higher. We have to be able to interpret these things properly, and we have to be able to put them back into context. When we're doing that, and when we're looking for rate of change, that's the key thing. It's actually fairly straightforward once you start working at it and get your head around it. Take the derivative, substitute in your value, and find out what your answer is. If there's a context, put it back in with the correct units, or the correct information. You have to be able to do this.